Hey YouTube, I was messing around with some bone conduction headphones when I was reminded of beat frequencies. Beat frequencies occur when you have two tones playing that are very close frequencies. The two tones alternately interfere with each other constructively and destructively to make a beating kind of sound, where the volume of the two tones increases and decreases over time. In this video, I'm going to go over why beat frequencies happen and show you a couple examples. For the first example, I've synthesized two tones, a 240 Hz tone and a 241 Hz tone. First, the 240 Hz tone. As you can hear, there is no apparent change in the pitch or volume of the tone. Next, the 241 Hz tone. Like the 240 Hz tone, there is no apparent change in pitch or volume. Now I will play the two tones together. That time, there is a very pronounced change in volume. This is the beat frequency between the 240 and 241 Hz tone. Now that you've heard a beat frequency, let's take a look at why it happens. I've put together this little simulation in order to have a more visual way to present this idea. At the top there are two signals which are superimposed over top of each other. Signal 1 is fixed at 50 cycles and signal 2 is variable. As this simulation starts, its frequency is 0 so that it appears to be a straight line. At the bottom of the screen I have the sum of the two signals, signal 1 added to signal 2. It just appears to be a sine wave because signal 1 is fixed and signal 2 is 0, so there is nothing being added to it. As I start the simulation, you'll see the frequency of signal 2 starts to increase. As it approaches the frequency of signal 1, you'll see that these lumps start to appear. These are the changes in volume we hear when two audio signals approach the same frequency. Eventually, when both signals are the same frequency, we find that they add completely, causing the output signal to have twice the amplitude of the original signal. Allowing the simulation to continue, the frequency of signal 2 drops down, allowing us to see those beat patterns again, and then it inverts, approaching the same frequency but with the phase inverted. When it reaches the same frequency, we find that the two waves completely cancel out, leaving no signal at all. Take a look at the two overlapping signals again, and you'll start to see why these beats occur. I'm going to pause it here when there's a very apparent beat, and I'll let you see the relation between the phase of the two signals and the amplitude of the sound that you would actually hear. The area circled in red shows the place where the two signals are completely out of phase with each other. The peaks and the valleys overlap, so that if you were to add a positive 1 signal to a negative 1 signal, you get a 0, which is why the amplitude of the output signal drops off to almost nothing. The area circled in blue shows a place where the two signals are almost completely in phase. This causes a +1 and a +1 to make a signal that's twice as loud, and a -1 and a -1 to cause an area that's twice as loud. These are both forms of interference, constructive and destructive, similar to the way that diffraction gratings work. Now that you've heard a synthesized sample and seen a visual demonstration of why this actually happens, let's listen to a real-world example. I have here two pop bottles of the same volume, except one of them has a couple milliliters of water in the bottom. I'm going to blow over them one at a time and see if you can hear the difference in pitch. The two bottles sound almost identical, but when I play them both at the same time, you can hear that beat frequency because their frequencies are just a few hertz away from each other. The beating is not as pronounced as in the synthesized example at the beginning of this video, but that's because the bottles don't produce nice pure sine waves. I hope you found this video interesting. If you'd like to see more like this, check out my channel. Thanks for watching.